Hi, this is Stewart. In today's lecture, we're going to talk about work in the physical sense, the science of physics. It's a quantity that describes force done over a distance, and the specific types of work we're going to be looking at are work done on springs and work done in emptying tanks. Okay, so let's get moving. First off, let's start by defining work. So work, in simplest terms, is force times distance. And you should note that this is true for constant force in the direction of the displacement. So in this little cartoon on the side here, you've got somebody pulling a 50 kilogram mass up 10 meters. So in order to determine how much work that person is doing, you would compute the gravitational force that you're opposing. So you have mass times the gravitational constant multiplied together. That gives you 490 newtons of force being exerted by gravity downwards. So you have to pull upwards with the opposite force, or 490 newtons. And then since you're displacing the object 10 meters upwards, which is in the direction of the force you're applying, you would get 490 newtons times 10 meters, or 4,900 newton meters. A newton meter is also called a joule, and I'll write that here. This is joule. Okay. So why do we care about force times distance? Well, when you measure the work applied to some object is equal to its change in energy. And there are two, depending on the context, types of energy. First is kinetic energy, so that's energy being expressed through movement. And that's measured, that quantity is equal to 1/2 times mv squared, where m is the mass and v is the velocity. And the amount of work tells us how fast the object is going to be going after the application of the force. The other kind of energy is potential energy. This is energy in terms of position in a field, which could be a magnetic field or a gravitational field or some other field. And the amount of work tells us how much more energy is stored in the new position in the field. Okay, so by measuring work, we can determine the new energy of the state. Okay, so we know that if you have a constant force being applied over some distance, all you need to do to measure the work is to multiply the force by the distance. But what if the force changes as it is being applied to the object? Okay, and here you have a picture of this little dot moving over some distance, and the force being applied to it is changing as it moves. So how can we measure the work in such a case? Well, this is the standard integral calculus approach. You approximate it by constant pieces and add up the work from each of the pieces with constant force. So one approximation is given in this picture, where the bar here measures the force, the approximate force in a particular interval, and you just get the constant piece of work for each of those constant force pieces, then you add them all up. And if you let those little intervals get smaller and smaller, your approximation gets better and better. So your work is going to be the integral from the initial position to the end position of the force with respect to the position, the displacement, f of x dx. Now we can move to spring force. An example of a force that changes as it is being applied to an object is the spring force. Hooke's law states that the force exerted by a spring to return to its natural length is proportional to its displacement. In other words, if x is displacement from natural length, then the spring force is F equals minus kx, where k is a fixed spring constant. The negative sign indicates that the force opposes the displacement. So if we have some spring, and we'll put it horizontally so we don't have to take gravity into account. So we have some spring here. It's attached to some object. If the spring is not stretched at all, then we say it's at its natural length, okay? So if the spring is happy to sit here, this would be called the natural length. And then if you stretch it, okay, so then it kind of starts feeling a little pressure to extend. Okay, so the distance from its natural, so let's say this is its natural length. Then this extension will be, this is called the displacement, and we'll call that x. And so the spring is going to be exerting a pressure, a force in the leftward direction, okay, opposing the displacement in the quantity minus kx, okay, where k depends on the spring. Okay, and if you had pressed the spring, so you push the object so that the spring is compressed, then it would oppose it in the same way. It would want to go back towards its natural length, so it would move in the positive direction. Okay. When stretching or compressing a spring, you need to counteract the force exerted by the spring at every instant. So your applied force is f of x equals positive kx, right? Because the spring is pulling back or pushing against compression. So you have to pull with the extension or with the compression. The work done stretching a spring from an initial position x init to x end, meters away from its natural length, will be W equals the integral from x init to x end of f of x dx, where f of x is kx, and k is in units of newtons per meter, and both x and dx are in meters. Okay, it's possible you'll have these expressions in the English system. I'm going to try to generally use the metric system. Okay, but something to be very careful about in this context is that the zero position in these computations must always be when the spring is at rest. So sometimes you'll see a problem where it says, a spring is stretched from 1 meter to 2 meters, and you'll say, okay, I'll just do the integral from 1 to 2. But what's key here is that you need to see how far it is beyond its natural length. So if it's 1 meter to 2 meters, but natural length equals 0.5 meters, then you have to change this integral. It shouldn't be 1 to 2. It should be the distance past natural length, 0.5 to 1.5. Okay? So that's something to be cautious about. Okay, let's do an example. A force of 10 newtons is required to hold a spring extended 1 meter beyond its natural length. How much work is done to stretch the spring, from rest to 1 meter beyond its natural length? Okay, so we have 2 bits of information. We have 1 bit of information, and we want to turn that into a bit of information about work. So let's first interpret this in an equation form. So we know that spring force F equals, or rather the force opposing a spring will be equal to kx, where x is displacement and k is the spring constant. So in our context, we have 10 newtons equals k times 1 meter. Rearranging, we find that k, our spring constant, is equal to 10 newtons per meter. Okay? Now we can use that to compute the work. So we know that the work is equal to the integral of kx dx from x initial to x end. In our case, this is from 0 meters to 1 meter. And we have k equals 10 newtons per meter. and x is given in terms of meters, and dx is also given in terms of meters. So we just include the units to make sure that everything has the right units at the end. And if we look at what happens to these units, one of the meter in the denominator here cancels with the meter in the numerator here, and we get one other meter. So our answer is going to be in Newton meters or joules. And the integral here, 0 to 1, of 10x dx equals 5x squared from 0 to 1 Newton meters, or 5 Newton meters or joules. Okay, so the work done is 5 joules. Okay, let's review what we did. We used the first bit of information here to derive the spring constant. And then once we had the spring constant, we could compute the work. Okay. A second example we'll look at is here. You perform 1 joule of work to stretch a spring from a length of 2 meters to a length of 3 meters, and another 2 joules to stretch the spring from a length of 3 meters to a length of 4 meters. What is the spring's natural length? So let's draw the situation we're dealing with. Okay, so let's say we have our spring, and here's the mass, and we're saying at this point it's at 2 meters. And now we'll draw after the first stretch. This is 3 meters. And at the second stretch, that's 4 meters. Okay, so, oops. Okay, and we're saying that to go from stage 1 to stage 2 is 1 joule, and to go from stage 2 to stage 3 is 2 joules. Okay, so let's write down the relevant equations and see if we can extract some meaning here. So we know that the work for the first transformation is the integral it starts out at 2 meters, so it's 2 minus the natural length, and let's call that L, up to 3 minus L, and that's equal to the integral of kx dx, and the second work is from 3 minus L to 4 minus L, and that's kx dx. Okay, and we're going to be looking for, oh, I need to take some care here that, no, I think actually right now we're okay. So we're going to compute these two and solve for k and L, keeping in mind that this first one is 1 joule and this second one is 2 joules. Okay, so let's make a new slide to do this computation. Okay, clear the slide, and then we're going to go here. So if we call this integral 1 and this integral 2, so we have that from 1 we get k times x squared over 2 from 2 minus L to 3 minus L equals 1, and you should double check that all of the units line up. We're taking k to be in newtons per meter, x to be in meters, and 1 to be in joules. So that means that k over 2 times 3 minus L squared minus 2 minus L squared equals 1. Okay, simplifying, we get, we'll bring the 2 over k to the other side, and then we have 9 minus 6L plus L squared minus 4 minus 4L plus L squared equals 2 over k. And so we get so 5 minus 2L equals 2 over k. Okay, so this is one expression. This is one relationship between L and k. And now we'll do the same for the second integral. So we know that doing out this integral, we'll get k x squared over 2 from 3 minus L to 4 minus L equals 2. And again, double check your units, but everything lines up here. This means that we have k over 2 times 4 minus L squared minus 3 minus L squared equals 2. And that gives us 16 minus 8L plus L squared minus 9 minus 6L plus L squared equals 4 over k. And putting it all together, that means that combining terms, so the L squareds cancel, and we have 7 minus 2L equals 4 over k. All right, so this is clearly twice of 2 over k, so that means that 7 minus 2L is equal to twice 5 minus 2L, and manipulating terms here, we get seven minus 2L, just multiplying out, 10 minus 4L, and that means that 2L equals 3, or L equals 1.5 meters. Okay, that was a bit of a journey, but we just used the 2 work computations to solve for what this natural length is. Okay, now we can go to our section on tanks and how we can talk about the work done emptying a tank. Okay, so we're trying to figure out how much work is required to empty a tank of water. And the way we're going to do this is start by taking it a molecule at a time. How much work is required to lift a water molecule out of the pool? Well, the force due to gravity is constant on the surface of the Earth, or approximately constant. So the work is the gravitational force times the distance to the top of the pool. Gravitational force is mass times g, the gravitational constant. So we get work as mass times g times distance to the top of the pool. Based on this, the work is a function of distance to the top of the pool because mass of a water molecule and the gravitational constant won't change for different molecules in the pool. Okay, so now we have to aggregate the work of lifting all of the molecules out of the pool. So the total work is equal to g, because since g is constant, we can factor it out, times the sum over all molecules of the mass times the distance to the top. Now to make this, so we don't want to take a summation over all molecules, so we're going to group together the molecules that have approximately the same distance to the top and treat the mass of each grouping as a function of volume. So the total work is equal to g times the sum over all slices at height y of the volume of a slice times the density of water. Okay, that gives you the mass of water in a given slice, times top minus y, meaning the distance you have to travel from the top down to where that slice is. Okay, and that's constant over the slice. Okay, the density of water, rho, is constant, so we can pull that out as well. And we can also write the volume as a function of the cross-sectional area, right? So think about, let's draw a pool, rectangular pool. So the volume of the slice here it has area A and thickness dy. Okay, just this tiny thickness so that everything is still pretty much constant distance to the top. Okay, so that the volume of that slice is A times dy. Okay, so we have this summation that the total work is rho, the density of water, times g, gravitational constant, times the sum over all slices at height y of the cross-sectional area times the thickness times the height of the top minus the y value. If we let the thickness of each slice approach 0, so now we're taking thinner and thinner slices, letting that dy become an infinitesimal, we find the summation approaches the integral from 0 to h water of rho times g times a of y times h top minus y dy, where a of y is the cross-sectional area at height y. That's in units of length squared, possibly meters squared or feet squared. Rho is the density of water. This will be kilograms per cubic meters, perhaps. G is acceleration due to gravity. Think of that as meters per second squared. dy is the infinitesimal thickness or length, and that's in meters. H water is the height of the water. So that's the top slice that you're going to be looking at. That's also in meters. And H top is the height of the pump out pipe. So that's what you'll be using in terms of how far am I lifting each slice of water. So that's also in meters. Okay, and filling in the other corresponding English units, feet, feet, feet. Meters per second squared corresponds to feet per second squared. And kilograms per meter cubed, that's going to be, I forget the English unit that corresponds to that. But if we need it, we'll come to it. We're going to try to stay metric because it keeps things overall much less complicated. Okay, so let's do an example. Consider a rectangular pool of depth 3 meters, length 50 meters, and width 25 meters full of water. How much work is required to empty the pool from the top? Okay, so we have our pool. Okay, so this is 50 meters. This is 25 meters. This height is 3 meters. And it's full of water, and we're taking the height of the pump out pipe, so I think it's H top. That's going to be just the height of the water, which will be 3 meters. Okay, because we're emptying the pool from the top. Okay, so let's take this integral I don't know if we can actually drag this integral. Yeah, probably not. Well, let's just rewrite it then. So we know that the total work is equal to the integral of rho g a of y h top minus y dy, where you go from 0 to the height of the water. So for us, this is going to be integral from 0 to 3 meters of rho, and the density of water is 1,000 kilograms per meter cubed. Okay, and that's something that will be provided to you if you need it in a problem. G is given by 9.8 meters per second squared. A of y, so now we have to compute the area of a cross-section. So we'll note that A of y, this is a rectangle with dimensions 50 by 25, so it'll be equal to just 50 times 25, which is 1250 meters squared. Okay, so we can multiply that in here as well. And then h top is 3 meters minus y dy. Okay. So from here, it's relatively straightforward. We'll bring everything out in front. So we have 1,000, all of the constants come out in front, times 9.8 times 1250 times the integral from 0 to 3 of 3 minus y dy. And this is clearly the same expression here, and then this, you take the antiderivative, you get 3y minus y squared over 2 from 0 to 3, and that gives us, okay, this same constant, I'm just going to call this c for now, c times 9 minus 9 halves, and then the 0 term vanishes, so this is obviously 9 halves, and we get 9c over 2, where this is c. And that will be our work for emptying this rectangular pool. Okay, let's do one more example. Consider a spherical tank of radius 5 meters with an output pipe positioned 1 meter above the top of the tank, as pictured in this picture I found on the internet. How much work is required to empty the tank? So let's start by naming some of our variables. And in this problem, I'm going to use z as our height coordinate because it's a little easier to describe the situation that way. So we have z equals 0 here at the bottom of the tank. And then at the center, we'll have z equals 5 because the radius is 5. And up at the top here, radius, the z value is 10. Okay, and that means that this is z equals 11. So if we assume the tank is full of water, we have the height of the water is 10. And h top, the place where the water leaves the pump, is at 11. Okay. What we need now is the area of the cross section at height z. And to do that, we're going to note that the cross section at height z is a circle. So this vertical distance is 5 minus z, and then this horizontal distance is kind of an x squared plus y squared, square root of x squared plus y squared, where the x and y are the horizontal coordinates. So to find the cross section, so to get the circular cross section, to get the area, we'll need the radius. So because we're looking at a spherical tank, this is a sphere with center given by 0, 0, 5. So that means that the equation is given by x squared plus y squared plus 5 minus z, or rather, apologies, z minus 5 squared. It's equivalent, but let's just keep standard form. And that's equal to the square of the radius, which is 25 meters squared. So if we want now to solve for this radius, which is square root of x squared plus y squared, we'll subtract the z term to the other side. So we get x squared plus y squared equals 25 minus z minus 5 squared. And we can take the square root of both sides. And what we obtain is that this radius, which we're interested in, is given by the square root of 25 minus z minus 5 squared. Okay, and you'll notice that at z equals 0 or at z equals 10, this radius is 0, which lines up with what we see, because you have just a point there instead of a circular cross-section. And at z equals 5, you have radius of 5, which also lines up with what we see. Okay, so given that that's the radius, the area will be pi r squared, or pi times 25 minus z minus 5 squared. Okay, and to simplify that a little bit, this is pi times the 25's cancel, and we're left with 10z minus z squared. Pi times 10z minus z squared. Okay, let's make a new page to finish out the integral. So recall that our formula here is that the total work should be equal to integral from 0 to the height of the water of rho g a of y h top minus y dy. Again, we're using z here. So the work is going to be equal to the integral from 0 to 10 meters of rho g, so these are constants that we'll fill in later, times the area of a slice, and that we just saw that that's pi times 10z minus z squared, times h top minus the z coordinate, so that's 11 minus z d. And you should make sure that all of the units line up, because we've been working in meters this whole time. We're in fine shape. So this is rho g pi times the integral is from 0 to 10 of 10z minus z squared times 11 minus z. Let's see if we can simplify that. So we have z. We can factor out one of the z's here to make it a little simpler. And I'm going to reverse both signs so that it's a little easier for me to multiply. Z minus 10 times z minus 11 dz. And that equals rho g pi 0 to 10. And now we're going to get z cubed minus 21z squared plus 110z dz. So continuing on, rho g pi times, taking antiderivatives, z to the fourth over 4 minus 7z cubed plus 55z squared, evaluated from 0 to 10. And that gives us rho g pi times, okay, so we have 10 to the fourth over 4, which is 2,500, I believe, minus 7 times 10 cubed, which is 7,000, plus 55 times 10 squared, 5,500, and that gives us, so we have 8,000 minus 7,000, so we have 1,000 rho g pi. And if you want to get that in units, so this will be again, we're using units of work. Everything was in the metric system, so we'll end up with joules, and we can use 10 cubed times, it's 1,000, the density of water is rho, that's 1,000 kilograms per meter cubed, so that's another 10 cubed, times 9.8 meter per second squared. And again, we're leaving out units, times pi, so this is, and that's in units of joules. So that gives us 9.8 times 10 to the 6th times pi joules. And that's the answer to this problem. Yeah. So the key to this problem was thinking what that cross-sectional area is. It's not constant like with the rectangular pool, it's constantly changing. But once you get the equation for that area, once you get an expression for that area, you're able to compute the integral with not too much difficulty. Okay, thanks very much.